Hello friends, welcome to Science Team. So far we have discussed different theories, philosophies about space and time to create a background for learning a special theory of relativity. We also discussed something regarding the history of a special relativity. Now we will start developing the mathematical background for learning a special theory of relativity. So we will start today with the Galilean transformation. So let's start with Galilean transformation. To understand Galilean transformation, just imagine two observers. One is at rest on the ground, which is S, and the other observer is in a vehicle moving with some velocity V. So this observer is S prime. We also call it reference frames. One reference frame is the ground and the other reference frame is this vehicle. A moving coordinate system is called a reference frame. So the problem is that we want to find how the coordinates of this point, any point in a space, will change with respect to these two observers. For this we will have to imagine a coordinate system. So imagine a coordinate system with three axes. This is X, Y and Z. Now for this observer we have a coordinate system which is S, and for that observer we will have another coordinate system S prime, and that coordinate system is initially at the same point. We will consider that both the observers were at same point initially, and after that it is at rest and it is moving with velocity. So initially both the coordinate systems will be at the same point. So S and S prime will coincide. Now after some time S prime will separate from S and it will be at a different location. So after some time, this is at t equals 0, and after some time it will be here. So now this point will have different coordinates with respect to the two coordinate systems. With respect to the first coordinate, let it be at a distance x, and for this S prime it is at a distance of x prime. The coordinates of this point P point will only change in x. There will be no change in y coordinate and x coordinate as this coordinate or the observer moves, because there is no motion in y axis and in z axis. The motion is only along x axis. So we know that the coordinate system is moving with a velocity v. So some time must have elapsed in moving from here to here. Now it's the assumption made by Galileo that time is a universal concept the amount of time elapsed is same for all observers in the universe. So for the S observer and for the S prime observer, both of them will measure the same amount of time. So T prime will be equal to T. This is the assumption made by Galileo. So the S observer will find that the S prime observer has moved with a distance of Vt, because in his frame he will call the time T, and this is moving with V velocity with respect to ground. So the distance will be Vt, and for the observer in the S prime frame, he will notice that he is at rest and the S observer is moving in backward direction, and he will say that the distance covered is Vt prime. So for this observer it will be Vt prime, and for this it will be Vt. So we will write x prime, the coordinates in S prime frame with respect to coordinates in S. So x prime will be equal to this distance minus this distance will give you this distance. So x minus Vt, or Vt prime, and in other step it will become x minus Vt. Now y prime will remain same and z prime will also remain same. Now if we want to write these equations in a matrix notation, then it's very easy. First you will have to write it in a simpler manner, like Vt plus x. I have just swapped these two things. Now it's very easy to write it in matrix notation. So we have our new coordinates t prime, x prime, y prime and z prime, and it will be equal to some matrix multiplied by t, x, y, z. Normally these things are written in a three-dimensional matrix, but I am writing it as a four-dimensional matrix because finally you will have to work in 4 dimensions in a special relativity. So I am using it since the start, so that after that it will be very comfortable for you. So now you have to get t prime equals t. So we will write here 1, 0, 0, 0. And now if it will multiply row into column, so you will get a t here. So here we have to multiply by minus v, so that minus v will multiply with t, and you will get plus x by putting 1 here, and this will be 0. And similarly we want y, so we will write here 1, and we want z, so we will write here 1, and the rest are zeros. So the same Galilean transformation equation, we have written it in a simpler in a matrix notation like this. If the situation is somewhat different, like this S is at rest here and the S prime is going in backward direction. Then the velocity, the direction of velocity is in negative direction. So the equations will change like this: t prime, x prime, y prime and z prime, and this will be equal to, the only change here will be in this equation. So you will have to write x prime equals x plus vt, because it is moving in negative direction. So the sign of v will be replaced by minus v, and that will be minus of minus v will be positive of v. Okay, so only this thing will change. So here will be 1 0 0 0, and this is v, and this is 1 0 0 0 0 1 0 and 0 0 0 1. So this will be the Laurent transformation equations in matrix notation. So now we will differentiate these equations with respect to time. So with respect to S observer, the time is t, so he will differentiate everything with respect to t, and you know that t and t prime are same, so differentiating with any of the t's will be same. So dx prime upon dt will be equal to, we are differentiating this equation, so we are having dx by dt minus v, and if you differentiate these two equations, you will get dy prime upon dt equals dy by dt, and similarly dz prime by dt will be equal to dz by dt. You can write these equations in a simpler manner like this. If we call this velocity as vx prime, so this is vx prime will be equal to vx, velocity of that point with respect to, as the coordinate system will move, they will notice that the points are moving. The point P will seem to be moving, and this is the velocity of those points. So this is Vx minus V. This will give you Vy prime equals Vy and Vz prime equals Vz. So this is what you get about the velocities in the two coordinate system. So you see that the velocities become relative in different reference frame. The velocity in the S prime reference frame is equal to the velocity in S frame minus the velocity of the frame. And since there is no motion in x, y and z direction, so the velocity both will appear to be same. Now if we again differentiate these equations, then what we get? So we will have d2x prime, or simply we have to differentiate this, so dvx prime upon dt will be equal to, now this is a constant, so the derivative of this term will be 0, so this will be equal to dvx by dt, and the same for all, dvy prime upon dt will be equal to dpy upon dt, and similarly dvz prime upon dt will be equal to dvz upon dt. So this is what you get on differentiation. So finally we conclude from here is that the derivative of the velocity, that is the accelerations of the two with respect to the two reference frames are same. So we can say here that ax prime equals ax, ay prime equals ay, and az prime equals az. Now if instead of the point, if we put a mass there at the point P, we are having some mass m, then multiplying m both sides will tell you that the force Fx prime equals Fx, we will multiply both sides by m, so it will be like m into Ax prime will be equal to m into Ax. And in Galilean transformation, we assume that the masses are absolute. It doesn't change with the observer. A mass will remain same with respect to any frame. So in S frame, either in S frame or in S prime frame, the mass will, both the observers will experience the same mass of that point object. So the forces will remain same. So similarly you can say Fy prime will be equal to Fy and Fz prime will be equal to Fz. So from here we conclude that the laws of mechanics remain same in Galilean transformation. So what we conclude from Galilean transformation is that the laws of mechanics remain same. Why we are calling like that? Because here the force. So we are giving some laws of dynamics. So we conclude from Galilean transformation that the laws of mechanics remain same for all inertial frames. So we are using the word inertial frame, and inertial frame means a moving coordinate system or a frame which is moving with a constant velocity with respect to a distant star or something like that. Now we will discuss the concept of invariant in Galilean transformation, and this we will extend in 4 dimensions in Lorentz transformation in special relativity. So it is a good idea to be familiar with the concept of invariant in Galilean transformation. So we have to understand this, let's imagine 2 coordinate systems S, and there is another system which is S prime, and this is moving with a velocity v with respect to S. Now consider a rod whose length is L and it is parallel to the common x-axis. So this is the x prime axis, this is x axis. So the ends of the rod will have different coordinates. With respect to the S prime frame, we will have x1 prime, x2 prime, we will have x1 prime, y1 prime and z1 prime as one coordinate of one end, and the other end's coordinate will be x2 prime, y2 prime and z2 prime. So if we apply Galilean transformation equations at the 2 ends, we can write it like this. So for the first end, and this is the second end, for the first end we have x1 prime, t prime equals t prime is same for as previous. So x1 prime will be equal to x1 minus Vt. y1 prime and z1 prime will remain same. With respect to this coordinate system, these label of the primes will not be there. So for this coordinate system, the coordinates will be having no label of prime, and for the other end we have x2 prime, y2 prime and z2 prime. This will be equal to x2 minus vt. y2 remains y2, y2 prime remains y2 and z2 prime remains z2. Now if we write it in and t prime will be t prime t and t prime will be equal to t for the two ends. Now if we write it in matrix notation, then it will be like t prime, x prime, y prime and z prime. Now put 1 1 1, and you know that this is minus v 1 0 0 multiplied by t x1 y1 z1. And similarly for the second end we can write t prime equals x2 prime, y2 prime and z2 prime will be equal to the same matrix here multiplied by t x2 y2 and z2. So we have Galilean transformation for the ends of the rod. Now if we subtract these two matrix equations, then we will have, so t prime minus t prime will be equal to 0, and we have x2 prime minus x1 prime, y2 prime minus y1 prime, z2 prime minus z1 prime. As the two matrices are same, so it will be common, and we have 1 0 0 0, then we have minus v 1 0 0 0 0 1 0 and 0 0 0 1, and this will subtract, these two will subtract, so we have a 0 here, and x2 minus x1, y2 minus y1 and z2 minus z1. Now since we know that the rods, the end of the rods, the rod is parallel to x-axis, so y1 and y2 will be same, so y1 is equal to y2, and similarly in the other frame y1 prime will be equal to y2 prime, and same for z1 equals z2 and z1 prime will equal to z2 prime, because it is parallel to x-axis, the rod has been placed parallel to x-axis, so these things will become 0. So we will write it as 0 x2 minus x1 prime prime 0 0, all will be 0. We are just developing a habit of writing in matrix form. 1 0 0 Otherwise you can write it without any matrix and it will be much simpler. So this is minus v 1 0 0, this is 0 0 1 0 and 0 0 0 1, and it will be 0 x2 minus x1 and 0 0. So the only equation that remains is x2 prime minus x1 prime equals, we will multiply this. When you multiply this by this, all the components will be 0, and when you multiply this with this, then you will get something. So we have x2 minus x1, because this will multiply with 0 and only 1 will survive by multiplying with x2 minus x1. So this is what you get. So you can say that the length of the rod, the difference in the coordinates, this is your x2 minus x1, remains same for both the observers. The observer in the frame S will measure the same length, that is x2 minus x1, and the observer in the S prime frame will measure the same length, x2 prime minus x, because both are equal. So lengths remain invariant in Galilean transformation, and laws of mechanics remain same for all inertial frames. So these are the two conclusions which we have arrived till now. So we arrived on a concept of invariant, that something which remains same or remains invariant in a transformation is called an invariant quantity, like the length of the rod which remains same in a rest frame or in a moving frame. Both the observers will measure the same length. So length of a rod is an invariant in Galilean transformation. Now the Galilean transformation is complete, but we will discuss a more problem, so that what we have learned till now, we will clearly see how to apply those things. So consider the two frames again. This is your S and the S prime frame, but now this time this frame is not moving parallel to x-axis. It can move in any direction, like this. The frame is moving with some velocity v. So how we will apply the Galilean transformation? So we will resolve this velocity in three components, Vx, Vy and Vz. So for time, you already know that the time remains same in both the frames. Now this velocity has three components, Vx, Vy and Vz. So in x-axis we will have the following Galilean transformation: x prime equals x minus Vx t. This velocity can be written like this: v equals Vx I cap, where I, j and k are in x, y and z direction, plus Vy j cap plus Vz k cap. So, and for y prime we will have y minus Vy t, and for z prime we will have z minus Vz t. So now you are seeing that the Galilean transformation has been applied in all the three axes. Now we will write it in a matrix form like this: t prime x prime, y prime and z prime. We will always be in a habit of writing these things in a matrix form. T, x, y and z. Now we will write it in this form: minus vx into t plus x minus vy into t plus y and minus vz into t plus z. So we will write, we will give preference to the t term because it will always come first. So now we will write, we have to get this one from the matrix. So the first thing is that, which is same. Now for x, you will put here minus vx 1 0 0. Now you will get the what you want, as it will be multiplied with this. You will get t into minus vx and x into 1 will give you x. Now for the y term, this will be 0. No, this term will not be 0. Here we will only we will write here minus vy, then 0, then 1, then 0. And similarly for z, we will write here minus vz 0 0 and 1 here. So in this way we will write our Galilean transformation equations. Now again, if you put a rod here like this, and the two ends are x1, y1, z1 and x2, y2, z2, then the coordinates will again change, and we will write the Galilean transformation equations like this. We are just converting for this one, this is 1 and this is 2. So we will have to put a subscript 1 in a here. Not for t1 and t2 will be same, so you can just avoid writing this 1 here and this 1 here. So this is y1 and z1. And similarly you have to write for the other end, which is t prime, x2 prime, y2 prime and z2 prime equals the same matrix multiplied with t, x2, y2 and z2. Now just subtract these matrices and you will get 0, x2 prime minus x1 prime, what we get previously, y2 prime minus y2 prime minus y1 prime and z2 prime minus z1 prime. This is equal to the same matrix into 0, x2 minus x1, y2 minus y1 and z2 minus z1. Now suppose that the length of the rod is very small. The rod is very small and its length is not L, it is delta L. The length of rod is very small, which is delta L. Previously it was L. So instead of writing x2 minus x1 prime, we can write it as delta x. So we will write it as, this is 0, this will be delta x prime, delta y prime and delta z prime. Now this small length, we are assumed that we know that it will remain same in both the reference frame, but we are calling it with some another label prime. So in the primed frame, the length of the rod is delta L and delta L has three components. Delta L has delta X, delta Y, and delta Z. Like this is the rod delta X. So its X component will be, this is delta L, delta X. This Y component will be delta Y, and similarly the Z component along the projection on Z axis. So you can write it in vector form as delta L equals delta X I cap plus delta Y J cap plus delta Z K cap. So this will be equal to the matrix 1 0 0 0 minus Vx minus Vy minus Vz 1 0 0 0 1 0 and 0 0 1 into 0 delta X delta Y delta Z. So this small length will remain invariant because this is the transformation matrix. Now we will start calling it a transformation matrix for the Galilean transformation. This was the old component of the length and this is the new component of the length. Whether you call it not old or new, it's in the S frame and this is in S prime frame, and this is the transformation matrix, Galilean transformation matrix. So in this way you write the Galilean transformation equations. Now if you multiply the two matrices, we get 0 delta X prime delta Y prime and delta Z prime equals, this will give you only 0, this will give you delta X, this will give you delta Y and delta Z. You came in conclusion that delta X prime equals delta X, delta Y prime equals delta Y, and delta Z prime equals delta Z. So this is what you get. So we conclude that the components of the length of the rod along the three axes with respect to the two frames remain same. So this is what we get from the Galilean transformation, and we can say that the length remains invariant whether we move the coordinate systems parallel or in any direction. In the previous example, the S prime frame, the X axis were moving in the same, the X prime axis of the S prime frame was moving parallel to the X axis of the S frame, but in this example it is moving with some arbitrary velocity, but that velocity is constant. Because that velocity of the S prime frame is constant, so it is an inertial frame for the S observer, and we know that in Galilean transformation the length remains an invariant. So this delta L is invariant for the two observers. So if these three quantities are same, then we can we write it like this? So delta X prime plus delta Y prime plus delta Z prime equals delta X plus delta Y plus delta Z. Is it true? So it is numerically true, but we do not write it in this form, because in some cases, like in case of rotation, just adding the three quantities will not give you the same quantity. So we will see this in our next lecture. So please like our video, share our video and subscribe to the channel, and thanks for watching.